which is Michael Kerrisk. Michael Kerrisk is the author of a highly praised book, The Linux Programming Interface, a guide and reference for system programming on Linux and Unix. Since 2004, he has been the maintainer of the Linux Man Pages project. Michael is in Munich, Germany, and works as an editor and writer at lwn.net.
Just give me a moment here. For some reason that slide deck didn't load. The slides that were scrolling before, if you happen to look at them, I'm not going to talk about those today. They were just to illustrate a point which I'm going to go into in more detail in this talk. The particular point there was that 30 years ago someone made a bad interface design decision that we are having to live with ever since. So when someone gets something wrong there in an interface, it's painful and it lasts a long time. And that's really the point of my talk. Okay, so I already had a bit of an introduction there, so I think there's probably not much more to say. I think it's just fair to say that I do spend a fair bit of time, or have spent a fair bit of time over the years looking at the Linux programming interface. And I've noticed some patterns, if you like. Now, my talk bounces off the title of a talk by Dave Jones. I don't know if Dave actually made it along here, but he did this talk about 5 or 6 years ago in Ottawa, first of all, I think. Was very amusing. Why user space sucks. And what he did was, his perspective was, you know, we kernel developers, we've made a fantastic kernel, it performs wonderfully, but, you know, can we make it go better? For instance, he wondered, why the hell does it take my machine so long to boot, or even to shut down? Or why does it take so long to start applications? When my laptop's running, why does it consume so much battery power? So he did some simple things to instrument the kernel to find out what it's doing. And he found out things like this. You know, on startup, 80,000 calls to stat, 27,000 calls to open, 1,400 programs executed, and some pretty remarkable stats on shutdown as well. And what he realizes is that user space programmers are doing crazy things, opening the same file and reparsing it sometimes dozens of times, reading config files for devices that aren't even present, and so on and so on. And he drew the obvious conclusion, which I think was somewhat influential, that there's a room for a lot of improvement, that people, user space programmers should start making use of a lot more monitoring tools to find out what their programs are doing and actually make them better. So tools like perf, systemtap, strace even, PowerTop, just get a greater insight into what their code is doing. Now, Dave Jones didn't say this, but you know, if you stood back, you could almost get the impression the world looks like this. Kernel space is paved with gold, and user space is a bunch of old lead. And as I say, Dave didn't say this, but you might conclude we kernel developers are much smarter than those crazy user space programmers. Or, as someone else put it, when they did some user space programming, but as far as I'm concerned, there is something wrong with this picture. And I want to question a couple of myths. The first one is that kernel programmers can always get it right, at least in the end. And the other one is that code is the best way always to contribute to free software. So the first myth, kernel programmers always get things right in the end. But there's one place that they can't, and they don't, and that is the interface between the kernel and user space. What I mean by this is things like system calls, pseudo file systems, IO-CTL interfaces, netlink sockets, and a few other more obscure pieces of interface that the kernel presents to user space. Mainly I'm going to talk about system calls for my examples. The thing is, interface designs pretty much have to be done right the first time. So there's not a concept of getting things right in the end. Okay? It's easy to change code, but it's hard to change APIs. Okay? If you put changes on a scale from easy to impossible, you might find that code changes fall anywhere along that spectrum. But API changes tend to fall much further to one side. It's often quite difficult to change an API, or it's impossible. Now, why is that? Well, usually if you change an API, that means breaking programs that already exist out there in user space. It's often very hard to change an API in a way that adds new behavior without at the same time breaking existing user space programs that already depend on a certain behavior. And it seems like Linus says this almost every week lately, some version of this statement. We don't break user space. It's actually worth just emphasizing that he says we don't break user space. He doesn't say we don't change the ABI, because sometimes actually we do in ways that are incompatible. But as long as something doesn't break, we're good. My main point, though, is when you do something in terms of an API, whatever it is, we have to live with it, including the mistakes. And an interface design mistake can create pain for thousands of user space programmers for decades. And the example I had scrolling there at the beginning was a 30-year-old decision that someone made that we live with to this day because the sockets API is so widely used. Now, if you had a very strict interpretation of ABI compatibility, you'd never change anything. You wouldn't even fix bugs no matter how bad they are. In truth, it's a bit of a grey area. You know, ABI breakages, they're measured against, well, how bad is it not to change things? If it's a bad bug, how painful is it? How painful is the bug versus how painful is it perhaps to break some existing applications? Or there may be very few users for the API, in which case, if we change it, maybe no one's going to get hurt. So what does it mean to get an API right? Just very quickly, these are some of the things I think of when I consider getting an API right. The obvious one, I suppose, no bugs. Make it simple, make it easy to use, make it consistent with other APIs that are similar to it, that already exist. It should integrate well with existing features of the kernel API. Okay, how does this new API behave with respect to fork or exec or threads or signals, file descriptors? It should be as general as it can possibly be. It should be extensible where that makes sense. It should adhere to standards if there are relevant standards. It should be better than what came before. And it should be maintainable over time. And the idea of maintainable over time is quite an interesting one, and I have what I find is quite an interesting example of an interface that isn't maintainable over time. So let's look at some examples, see how kernel developers actually do in terms of building APIs. So first of all, bugs. I don't test new interfaces quite as frequently as I once did, but when I was testing pretty much every new interface that came out for a while, I could usually find a bug in every second new system call that was added to the kernel. And these, I'm talking about the released kernels, not the RC kernels, but the thing that actually went out the door. So UTIME-NSAT, which was released in 2.6.22, which sets file timestamps, I found about four different bugs in it. In special corner cases where it wasn't doing the right thing in terms of setting file timestamps. That got fixed 4 releases later. So there were 4 kernel releases there where the bugs just lived. SignalFD, which was added in 2.6.22, enables you to get signals via a file descriptor. If you were using it with SIGQ, you didn't get the right data via your file descriptor. Again, it was 3 kernel releases before that was fixed. There are lots of other examples as well. I just mentioned a few there and a few URLs that point out the problems, or elaborate on the problems. So what's going on? I think there's a pretty significant quality control issue. It seems like most, well, no, not most, a significant proportion of interfaces go out the door and they're buggy, even in the stable kernel. There's not enough people doing testing. Unit tests are something for Java programmers, aren't they? There's insufficient test coverage, and perhaps most tellingly, there's no clear specification of what to test against. In other words, someone comes along, they code the new interface and put it out there, and they think they know what they're supposed to be doing, what the interface is supposed to do, but perhaps no one else does, because they haven't explained what the interface does, they've just released it. And the thing is, even if the bug is fixed, it still hurts users, because then you might end up with a situation where you've got a user space program that has to deal with the bug. It has a special case on the kernel version. So if I'm using the older kernel, I have to handle this bug, and if I'm using the later kernel, then I'm good. So it's bugs. Now, in terms of design, there's a whole lot of things that go wrong, I think. One of them is the phenomenon of what I like to call code it now, think about it later. Here's 3 system calls that have some arguments that nowadays they ignore. Read, dir, get CPU, epoll, create. At the beginning, someone thought we needed these arguments, and then a while later they realized they don't. Probably, if we thought about it at the beginning, we would never have had the arguments at all, okay? But there wasn't enough review of the design, enough thinking about the design to realize that at the start. Another example, there is a system call in the kernel fu times at, which was added in 2.6.16, sets file timestamps. It was actually proposed for POSIX 2008. It was implemented on Linux at the same time, and the POSIX committee realized this interface isn't sufficient. So they standardized a different one, which is utime nsat, which we added in 2.6.22. Another example, in 2003, Linux 2.6 added epoll wait. Okay, this is about file descriptor monitoring. It's an improvement on the select system call, which has been traditional on Unix systems for about 30 years. It had one limitation, and that limitation was addressed in kernel 2.6.19 when we added a new system call called epoll pwait, which allowed us to monitor file descriptors, multiple file descriptors, safely in the presence of signals. Okay, the idea was that you could do a poll which at the same time unblocked some signals. It's a superset of epoll wait. Okay, seems like a good enhancement to have. The thing is, there was already, back in 2001, an interface in POSIX called pselect, which was the exact analog for select. It did the same thing that epoll pwait does compared to epoll wait. Okay, pselect is to select the same thing. That was in 2001. Why then didn't we already know to do things right the first time? We didn't need epoll wait. We already knew the problem. We could have had epoll pwait at the start. Consistency of design. Okay, this is one of my favorites. The mlock system call. It locks a piece of memory into RAM. Simple interface. You say the start address of the range you want to lock, the length that you want to lock. Start is rounded down to the page size, length is rounded up to the next page size. All sounds very sane and rational, so when you say mlock 4,000, 6,000, assuming a page size of 4K, you lock bytes 0 through to 12K. Then, in 2.6, we had remapped file pages. Same arguments, start and length. Round start down to the page boundary. Okay, good. Round length down to the page boundary. When you say remap file pages 4,000, 6,000, what do you get? Actually, it's even worse. I hasten to add that this is one of the top kernel developers that did this. Okay, well, I don't need to name names, but even the smartest kernel developers do this. And when you have this sort of inconsistency, programmers expect interfaces that look the same to behave the same. And when they don't, they write bugs. Okay, if you write a remapped file pages call in the expectation that the arguments are the same as mlock, and they're not, well, you've inadvertently created a bug in your program, of course. Okay, more on the line of confusing the users. Okay, there are various system calls that require privileges. These are system calls that change, one process can change the attributes of another process. Those calls either require you to have privileges, some capabilities, or there is some sort of credential checking performed, so that some combination of the caller's UIDs and GIDs match some combination of the target process's user IDs and GIDs. But there's a lot of inconsistency, okay? And here, when I've got things like here, a set priority that says to do a set priority call on another process, the effective UID of the caller must equal the real UID of the target process, or the effective UID of the caller must equal the effective UID of the target, and so on and so on and so on. My point, without drilling down into the details of each call, is that all of these calls do it differently. Okay? And the last one, indeed, is quite complex. And this is inconsistency that confuses the users. And furthermore, it's inconsistency that confuses the users to do with credential checking. So then you've got the potential for security-related bugs. I'll just pause so you can have a drink. Is there any questions so far? Willie.
Given the nature of those 4 different system calls you just put up...
That's not all of them, by the way.
Might there be some justification for actually having different permission checks? Or is this just simply stupid?
I think it's just simply stupid. It's something that springs out of the design model, where everybody invents a new thing and they don't necessarily go back and check what already is done. And in part, it's not, well, what it would be nice, as I answer this question I realized would be, is if all of this was documented in one place. Yeah? Who knows, maybe I'll add a man page for that. And maybe some people will read it, though I'm not sure. Okay. I mean, the kernel developer's perspective is often man pages are for users. Yeah? I'm surprised about the number of people who don't know about the capabilities man page, for instance, and I'll come back to that example later on. Okay, another kind of problem in interfaces is making them sufficiently general. Okay, in Linux 2.6.22, there is a new system call called timerfd. It basically enables you to create timers that notify via a file descriptor. So it's just a different way of doing timers. The point is, if you have a file descriptor, you can give that file descriptor to a call like select or poll or epoll wait, and you can wait for that file descriptor with all of your other file descriptors as well. So it's a nice idea. But the API that was there originally was quite limited. one thing you couldn't do was retrieve, you might have an existing timer whose value you change, but you couldn't retrieve the previous value of the timer. And you couldn't do things like saying, well, how much time remains on this timer at the moment? And the older POSIX APIs and the older Unix APIs already had that sort of functionality. You had get iTimer and set iTimer, which would enable you to change a timer and at the same time retrieve its previous value, or retrieve how much time was currently outstanding on the timer. A little bit of battling with the developer of that API meant we eventually fixed it. It actually, in this form, it did actually get released in the kernel in 2.6.22. But in 2.6.23, it was killed. And then by 2.6.25, it was done right. 3 calls, one to create a timer, another one to set its current time, and at the same time, if you wanted to retrieve its current, its previous timer value, and another one to say, give me the available time remaining on this timer. Same sort of thing as POSIX timers. Now, in theory, that was an ABI breakage because there was an old system call that was there for a release, but it went away. But essentially, that never got released or never got used by userspace. It never got exposed by glibc, and so no one in practice actually had a chance to use it. Do we learn from the past? So back in Linux 2.4, we had dnotify. This is an interface that lets you monitor files or directories to see if there have been changes. It had a lot of problems. One kernel developer cruelly said that the D in dnotify stood for suck. So we instead added a new interface, which was much nicer. It's not without its problems, but it is much nicer, called iNotify. But then in 2.6.37, we added yet another interface which did many of the same things. It was designed for virus scanning type software, because we have so much of that on Linux. It was called FA-Notify. Now, I have no particular opinion about whether we needed the extra functionality there. But my point is that in terms of functionality, here we had iNotify, and here we had FA-Notify. There's a lot of overlap in the functionality. We already knew there were some problems with iNotify. When we did another interface, why didn't it do all of the things we wanted and fix the problems as well? Okay, making interfaces extensible. This is a common design pattern in the kernel. We have an early system call that didn't allow for extensions. And then our solution was to add a new system call. So we started off with umount, we added umount2, which did some extra things. We had epol create, realized there was a mistake there, so we ended up with epol create2. A lot of these things you don't see at user space level, by the way, because the C library wrappers actually switched to using whatever the new version of the system call was. But underneath, the kernel has multiple versions of these system calls. We had FU times AT, which I mentioned already. Now we have U time NSAT, signal FD, and now we have signal FD4, and so on and so on. These system calls were all fixing a problem in the old system calls by adding a flag, which allowed behavior to be tailored during each call. So I think this is a lesson that we need to learn, which is when we're adding a new system call, we should always consider, is it useful to add a flags argument to allow for extensions? Okay? Whenever I see a new system call, if I happen to see it, I don't always see them, but I always think about that nowadays and pester people. And there was one success story there, Finite module, which is in the kernel that's about to be released, got a flags argument when I prodded people about it.
You say unused, but of course it can't be unused. You've got to check that it's 0 and return an error if any.
I'm going to come to that. I'm going to come to that. I'm going to come to that. Don't steal my thunder. Here we go. If a system call has a flags argument, then the implementation of that system call should always have a check like this. If flags and the complement of what's possible, if any other flag is set, if any other bit is set other than the flags I know about, give an error. Okay, and the point then is that if you add new bits with new functionality later, then user space can easily tell what is possible, because if they make a call that specifies the new flag on an old kernel and they get back an inval error, they know, oh, this is a kernel that it's an old one that doesn't have this functionality that I want.
This isn't the first interface we've used this on. This technique was first used with allocate
Okay, I tend to describe that as, when interfaces don't do this, I call them loose. Have I gone through all this now? Okay, I've said this basically. That was my point described before. Of course, kernel developers would never not do this, would they? Now, this is not a complete list of the system calls that fail to have this check. It's a sampling. Okay, the list is actually quite long, as I suspect Dave Jones has discovered with his Trinity tool. And then we've got a little problem. Well, if the check isn't there in some old system call, what do we do about it? Well, do we add it after the fact? You might do. That was done with umount 2. It added the check, which was added in kernel 2.2. It added the check in 2.6.34. Timer FD set time. 4 releases after it was added, it added the check. What's the problem with adding the check? So there might be some applications out there that are feeding in random bits to the flags argument in system call, and those random bits were never bothered about before. But now, with the check, those applications are going to break. So you're taking a chance, and this was the strategy that was pursued, basically. Let's make the change and see if anything breaks. No one complained.
Should handle the error anyway.
Sorry?
The application should handle the error anyway.
We don't break user space.
But that should mean we'll leave the bugs in.
But see, in effect, this is not a bug.
You allow the user space bugs to continue.
Well, this is the choice. Do we allow the user space bugs to continue? Or do we try and fix it in the hope that if we fix it now, maybe we won't have the problem in the future? Okay, these were 2 cases where it was successfully done. But when you do it, you might break the ABI. And applications get errors where previously they didn't. ePOL control, I have to look at all the details here. It added a flag. What was the name of the flag? It's quite recently. It was something to do with blocking. Hang on a second. I might just have it in my notes. Okay. If you can see that. Okay, you can't see that. It added a flag called ePOL wake up. If the caller has cap, block, suspend, it was a way of saying don't let the system be suspended during this call. Now, without going into the details of that, my point is, my point is, there was this flag. In order to use that flag, you needed to have a capability, and if you didn't have the capability, the system call gave you an error. Nice thing. The problem was that these flags to ePOL control didn't have that check that I described just before. And someone out there found an application that broke. And so the consequence was that now with ePOL control, if you specify this flag, whereas formerly you needed the privilege, and if you didn't have the privilege you got an error, now it's if you don't have the privilege, the flag is silently ignored. Because then that program out there that used the bit that was formerly unused no longer breaks. It just silently proceeds as it did before. So this is the kind of problem you have when you don't add these checks, or when you perhaps try and add them. So loose APIs, what I say about it is when you have a loose API, the user gets to define the interface, not you. Because they can make use of all of these random bits that you didn't use. And in the worst case, you can't add new flag values to the interface. Future-proofing, other kinds of future-proofing problems. Okay, these ones are easy to find. 16 bits is enough for user IDs, except it wasn't, we discovered. 32 bits is enough for file offsets. Well, it was 1991, but these things, disk drives do get bigger. So in 2.4 we had 64-bit offsets. And so we have a whole bunch of system calls now that essentially reproduce functionality but handle these changing sizes of data types. This is one of my favorite examples because it almost doesn't seem like a problem in interface design until you think about it some more. A traditional Unix system has this idea of root. Root has all privileges, everyone else has no privileges. It's the traditional model. It's kind of risky though, because if you give someone root, then they can do everything that root does. Someone came up with this nice idea, or so it seemed, of capabilities. Divide the privilege of root into separate pieces. So you might have a privilege that says, you can reboot the system. Or another one which says, you can send signals to any process on the system. Okay, instead of giving someone root, which lets them do all these things, you say, well, you have cap kill, allowing you to send signals to anyone. There's a trade-off there. You want to split your root into meaningfully separate pieces, but you don't want so many pieces that it becomes unmanageable. Okay, you could have hundreds of capabilities, but then it becomes pretty difficult to manage from an administrative point of view. This is slightly out of date now, of course, because we're up to 3.8. But Linux 3.2 had 36 capabilities. You might be able to read them up from up there. The point is just that there are 36 of them. And you're a kernel developer that comes along and you say, well, I've got a new system call. It should be one that is only executable by a privileged user. Gee, which capability do I use? Or do I add a new one? There are 36 of them in the list there. Let's walk through them. There's one there called nicely cat sysadmin. Hey, systems administrators are going to do the thing that I'm talking about, that I'm adding. That's the privilege I'll use. The new root is cat sysadmin. 451 users in the 3.2 kernel out of 1,167 total users. In other words, if you give someone capsys root, you've given them so many privileges that you may as well just make them root anyway. My point is that this almost doesn't seem like a design problem. The design problem, wow, time is flying. The design problem is in terms of how should this interface be maintained as we're going forward. Someone came up with this idea of capabilities and seemed like a good idea, but then capabilities are only going to work if someone's going to watch what is done with the capabilities in the future. You know, as a new system call comes along, how is it being allocated to a capability? And there is no central organization like that for capabilities. There is a capability 7 man page nowadays, which is moderately up to date even. I'm not sure how many kernel developers read it though. Okay, did we really need to do that? Well, This is a good quote from Linus. Probably the most common ABI change that we made was something we didn't even mean to make it. And no one knows that it broke, and it just stayed. There's a lot of examples of that. One of the ones I discovered quite recently, R-limit CPU resource limit. It's a limit on how much time a process can use. If you exceed the limit, there's a soft limit, then you get a SIGX CPU limit, a signal. If you hit the hard limit, you get a SIG-kill signal. Linux delivers the SIGX CPU limit signal on hitting a soft limit, and every second thereafter. But suddenly in 2.6.1, two things changed. Not only did you get the signal, but at the same time the kernel raised the limit, the soft limit, by 1 second. I have no idea why that happened. But the point is, if you've got a user space application that happened to be monitoring its own soft limit, it's going to see it's suddenly changing. Okay? It's not standard, it's surprising, it's non-portable, no one wanted it, it just happened. And it was probably unintentional. How many minutes do I have now? 7, okay. I'll have to be very quick. We sometimes randomly don't follow standards. POSIX says that the set scheduler system call should return the previous policy of, when you set a policy with set scheduler, Linux says always returns 0. There's no good reason for that. It's just the way we happen to do it. People, when they code for Linux, have to special case for Linux because of that. Okay, it wasn't just us, of course. We're following on a long tradition. System calls that return -1 on success. That's a whole brokenness in the Unix API design. System 5 IPC, its API is a disaster. These are things that all predate Linux. F-control locking is a disaster when you come to doing it with libraries. Select modifies its descriptor sets in place. The one example I had rolling there at the beginning, the socket sum path for Unix domain sockets, it's a mess. So we could be doing a lot better at API design. And why do we keep having these problems? Well, I think there's an extreme focus on code as the means of contribution to a project. And coupled with that, there's a poor feedback loop between the users of the software and the creators of the software. So the point is, a system call is added to the kernel. Often, users don't even know about it. Some particular kernel developer, or perhaps a few kernel developers, add the system call to scratch their own itch. And by the time it makes its way out into the wider world, it's already an established part of the ABI that can't be changed. And the problems that are discovered after that, it's too late to fix them. So there's my myth too, is that code is always the best way to contribute to free software. The classic line, show me the code. But anyone can write code. If it's bad, it can usually be fixed. But an API, if it's bad, it's very hard to fix. So there are some other sentences that I think are at least, or perhaps sometimes more appropriate when it comes to looking at contribution. Show me the user's requirements. Is this just fixing some single developer's itch, or is it fixing multiple developers' itches? We've got to be aware of having too limited a perspective on APIs. Is it general? Is it extensible for the future? Show me the design specification. Okay, I'm getting too unrealistic, I suppose. But there's often no specification, which means you can't even evaluate an API in terms of what it's supposed to be doing. How do we know if what the implementation does actually matches what the implementer intended? If there's no documentation or specification, we don't. When you don't have a specification, how do you write a test? You can't. Writing documentation is a fairly natural sanity check I've also found for design. If you just write about your design, it often uncovers design errors, just that act alone. A man page, from my biased perspective, is often sufficient for this task. Write the man page before doing the implementation rather than afterwards. Nice quote there from Andrew. Okay, that programming isn't just about telling the computer what to do, it's about telling other programmers what you're doing. Show me the design review. Again, another one of those fantasy sentences. Did anyone else look at your API design? Is it simple? Is it easy to use? All those things that I talked about in the list before, extensible, following standards, blah, 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 blah. Did you test it? Honestly, I think that some system calls that have rolled out there, even the developer didn't test it. Did you write some tests as the developer? Did someone else write some tests? That's even better. Do the tests cover the reasonable cases? Do they cover the unreasonable cases that Trinity is going to come along and find later? As you wrote your tests, did you find your own interface easy to use? Because that's an interesting question as well. So, I think if you're a contributor to a software project, you shouldn't fall into the trap of just thinking that code is the only or the best way of doing things. And if you're a maintainer of a project, are you thinking about getting these other sorts of contribution, design, review, testing involved with your project? And that's it. Thank you very much. And do we have time for questions? There's some time for questions.
So I may have missed it, but what are your thoughts on the Linux test project, LTP?
LTP?
Yeah.
LTP exists, and it's good in as far as it goes, and it sometimes helps catch regressions, but often the tests only make their way into LTP, which doesn't have nearly as many people working on it as it needs to have, but the tests often only make their way into LTP sometime after the interface is in the kernel. So it's by that time, it's, the bug's already there. Or it's only going to find, well, it's going to find bugs, but there's a whole bunch of other stuff I talked about as well in terms of design. LTP isn't about that, it's about finding bugs. But even then, the tests often come too late. One question up there. Oh, yeah.
Just a couple of comments. The first one, you might want to have a look at the NetBSD project about how they do their API versioning. To stop the proliferation of the syscalls. That could be an approach for doing that. The second one, when you were saying about checking your flags, again, a NetBSD developer had this idea many, many years ago, and he got shouted at after he'd done it because performance of checking those flags on frequently called system calls is very, very bad. And I noticed one of the ones that you had in there was for nanosleep.
Right.
And checking the flags every time through there is going to be a bit of an overhead. You'll be surprised how bad it gets.
Yeah,
Seriously, yes.
Try
it.
Okay, without actually having, without actually doing it. I mean, it would seem to me that the cost of the check is minute by comparison with the context switch.
Agreed. Yes, experience sells. Agreed. And this was exactly what the NetBSD developer who did this said. Nah, it's minimal.
Okay.
After he put it in, there were significant performance degradations, and he had to if-def or option out those calls so that you could do a special debug to put them in to catch those things and actually take them out for the production kernel.
Well,
seriously.
Okay. Even so, I'd argue against this, just because you can't extend your system calls otherwise. Willie down the front.
NetBSD runs on M68K. Perhaps that's where the 3 instructions became significant.
Right, and that's our time. So on behalf of the conference and Linux Australia,
Thanks, I already have one. So I already had a bit of an introduction there, so I think there's probably not much more to say. I think it's just fair to say that I do spend a fair bit of time, or have spent a fair bit of time over the years looking at the Linux programming interface. And I've noticed some patterns, if you like. Now, my talk bounces off the title of a talk by Dave Jones. I don't know if Dave actually made it along here, but he did this talk about 5 or 6 years ago in Ottawa, first of all, I think. Was very amusing. Why user space sucks. And what he did was, his perspective was, you know, we kernel developers, we've made a fantastic kernel, it performs wonderfully, but, you know, can we make it go better? For instance, he wondered, why the hell does it take my machine so long to boot, or even to shut down? Or why does it take so long to start applications? When my laptop's running, why does it consume so much battery power? So he did some simple things to instrument the kernel to find out what it's doing. And he'd find out things like this. You know, on startup, 80,000 calls to stat, 27,000 calls to... So there's not a concept of getting things right in the end. Okay? It's easy to change code, but it's hard to change APIs. Okay? If you put changes on a scale from easy to impossible, you might find that code changes fall anywhere along that spectrum. But API changes tend to fall much further to one side. It's often quite difficult to change an API, or it's impossible. Now, why is that? Well, usually if you change an API, that means breaking programs that already exist out there in user space. It's often very hard to change an API in a way that adds new behavior without at the same time breaking existing user space programs that already depend on a certain behavior. And it seems like Linux says this almost every week lately, some version of this statement. We don't break user space. It's actually worth just emphasizing that he says we don't break user space. He doesn't say we don't change the ABI, because sometimes actually we do. Open 1,400 programs executed, and some pretty remarkable stats on shutdown as well. And what he realizes is that user space programmers are doing crazy things, opening the same file and reparsing it sometimes dozens of times, reading config files for devices that aren't even present, and so on and so on. And he drew the obvious conclusion, which I think was somewhat influential, that there's a room for a lot of improvement, that people, user space programmers should start making use of a lot more monitoring tools to find out what their programs are doing and actually make them better. So tools like perf, systemtap, strace even, PowerTop, just get a greater insight into what their code is doing. Now, Dave Jones didn't say this, but you know, if you stood back, you could almost get the impression the world looks like this. Kernel spaces paved with gold, and user space is a bunch of old lead. And as I say, Dave didn't say this, but you might conclude we kernel developers are much smarter than those.
Is Michael Kerrisk. Michael Kerrisk is the author of a highly praised book, The Linux Programming Interface, a guide and reference for system programming on Linux and Unix. Since 2004, he has been the maintainer of the Linux Man Pages project. Michael is in Munich, Germany, and works as an editor and writer at lwn.net.
Just give me a moment here. For some reason that slide deck didn't load. The slides that were spread on before, if you happen to look at them, I'm not going to talk about those today. They were just to illustrate a point which I'm going to go into in more detail in this talk. The particular point there was that 30 years ago someone made a bad interface design decision that we are having to live with ever since. So when someone gets something wrong there in an interface, it's painful and it lasts a long time. And that's really the point of my talk. Okay, crazy user space programmers. Or, as someone else put it, when they did some user space programming, but as far as I'm concerned, there is something wrong with this picture. And I want to question a couple of myths. The first one is that kernel programmers can always get it right, at least in the end. And the other one is that code is the best way always to contribute to free software. So the first myth, kernel programmers always get things right in the end. But there's one place that they can't, and they don't, and that is the interface between the kernel and user space. What I mean by this is things like system calls, pseudo file systems, IOCTL interfaces, netlink sockets, and a few other more obscure pieces of interface that the kernel presents to user space. Mainly I'm going to talk about system calls for my examples. The thing is, interface designs pretty much have to be done right the first time.